You've just looked at two examples where our intuition for average allowed us to determine the average value of a continuous function. The first example was a constant function f of x equals c, where the average value is the value c. The second example was a straight line, and the average value over an interval from a to b is just the value in the middle. This middle value is the average of the values at the two endpoints, which is the value at a plus the value at b divided by 2. Note that this averaging of endpoint values only works because it's a straight line, but this averaging process also could work for the constant function that we had above, which is also a straight line. Of course, this midpoint won't work in general, but what will work is to connect the average value to the area under the curve. So let's focus in on this example with the straight line, and recall that the area under the line from a to b is how we defined the definite integral from a to b of this line. The area is the same as the area of the rectangle whose height is the average value and whose width is the length of the interval. So this is what we'll take as the geometric definition or the geometric explanation for the continuous average of any function f of x. So let's take a general function f of x. Then the average value of f, or the average height of f over the interval from a to b, is the value such that the area of the rectangle with width b minus a, and whose height is the average value, is the same as the signed area under f of x over that same interval. In other words, the average value of f, which I'll write as av f, so av f times b minus a, this is the area of the rectangle, and this is equal to the integral from a to b of f of x, which is the signed area under the curve. I'm going to let you use this geometric definition to find a formula for the average value of f in terms of the definite integral, and then we'll explain how this continuous average really does connect to the discrete average in a limit.